approach, solution approach that we've taken. And it's not exhaustive research that I present here, but just to give you a flavor of the kind of research that's done in research labs in the US, especially my labs. This is work done by my PhD students out here. And given the cloud computing and big data is very hot, and there's so much to study in it. So this by no way is an exhaustive list of research topics or solution approaches, but just maybe one. So just the motivation, we all know about big data now. Big data is being driven by the number of users that are using the internet that has gone up significantly over the years. So if you look at this figure, this is taken from this source here. Over the years, you can see how many users are now going through and using the internet. And this is a diagram that I've taken from this source. What happens is, when you have so many number of users, they're all generating different kinds of data. And that data is also increasing slowly and slowly out there. So this is one table. This is taken from Cisco. And they're talking about the internet traffic that has gone up over the years. And again, as you can see from 1992, which was a very modest amount in today's day, and look at their projection for 2021. This is unbelievable amount of data that will be flowing through the internet these days. So big data initially was, maybe say many years back, was supposed to be structured data, was data that you could store in, say, relational tables. And these are the classical data for, say, banks, when you have accounts and you have deposits and different queries that you could conduct, or even about students in a university. You could store them in databases and you could query and get information about it. Data is slowly and slowly getting, or more and more getting unstructured, which means data is coming as emails, data is coming as text, it's images, it's videos, it's all kinds of different formats, but you want to be able to extract information from it and then be able to query it. So those are needs that are going to produce some tremendous challenges in terms of technology, in terms of infrastructure. So once you have data at a massive scale, what changes is the data structures and algorithms and the computers that we're going to use. So the traditional data structures that we study in, say, computer science curriculum are data structures that will fit in memory. So what happens if you come up with a data structure and you want to use, but the data size is so huge that first it's not going to fit in just the local disk space. It's going to take thousands of computers with disk space. And the data structures that we're traditionally used to don't even work anymore because those will be exceeding the size of memory out there. So big data presents to us tremendous technical challenges in terms of coming up with new algorithms, new data structures that have to take into account that data is now spread so much, it's so distributed. So how do you come up with algorithms that take into account the network latency, the network throughput, and IOPS that you can get from disks, and different kinds of disks, flash arrays, so on and so forth. Now, just very brief, so my lab also does a lot of research in NoSQL. So just to give you an example of the growth of NoSQL these days, what NoSQL does is to let you store unstructured data. Again, data could just be documents. So they're essentially stored as key value pairs. Now, an important feature of NoSQL is that it provides horizontal scaling. So the basic idea is this: let's say you're running a very big multimedia company, or you're running some social media software, and you want to suddenly scale up from, say, 10,000 users to 100,000 users. Maybe 100,000 users to 1 million, 10 million. But this scale up is going to happen very quickly. So what NoSQL technology is, why it's getting famous or why it's getting more used, is the idea is you could simply add new servers to a NoSQL technology and then scale up quickly, which is not typically possible with an RDBMS. If you have a traditional like SQL Server or some kind of MySQL database, you cannot just add new servers and say, here, the whole thing scales up. But some of the constraints that were there in the normal RDBMS have been removed for NoSQL. So with NoSQL, with data being distributed, the idea is to get eventual consistency. You're not going to get consistency as soon as you write the data. And NoSQL, for example, Cassandra here, which was initially developed by Facebook, they're designed for writes. They're optimized to write data. For example, they're optimized for you to upload images. They're not optimized for you to read them very quickly. So they all have their own purposes. And the idea for eventual consistency is that eventually all the servers that are there across the world will have the correct copy of that image, but they may not have it at the same time. So it's possible for you to actually read an image at one place and not get this exact same image in, say, some other place. There may be some delay as the data is written and saved. So here the diagram that is actually being shown here, this is again a classical diagram for NoSQL here. The idea is that when you write an update, it's initially written to what's called a mem table. Mem table is because it's a table in memory. As we know, memory, it's much faster to read and write from memory as opposed to going to disk, where it becomes orders of magnitude slower. But there's so much data that you have to write it to disk. Writing is slow. So what you do is you write to memory using a mem table and keep logs of it. And in the background, it takes what's in memory and flushes it to the disk. That's how it gets its basic speed out there. And then there are lots of optimizations of what happens if it doesn't write, if you get an acknowledgement whether it's been written or not, what happens to the different servers because the servers are distributed, when will each of the servers get it, so on and so forth. But this is the basic model of NoSQL here in terms of consistency. Now there are many, many technologies out there. Some of the ones that you may have heard of are MongoDB, CouchDB, Cassandra, so on and so forth. So there are all these different technologies that are now catering towards this unstructured data so that they can save it, and they're optimized for different things. Some are optimized for writes, some optimized for reads. Then there are in-memory databases where you read from the disk, you keep everything in memory, but to make sure it is fault tolerant, what you do is you distribute it in memories of different computers. So if you have a cluster, each node's memory now has something, and then you replicate it amongst the memory of different nodes and try to get some fault tolerance there. So that even if one node fails, or if there's a network partition, you still have access to the data through different nodes. But then your application that is reading and writing data is still dealing with memory, which is orders of magnitude faster than the data, than reading from disk. Now disk is persistent there, but memory, once you put in memory, then how much you replicate, where you replicate, how far the different nodes from each other, what kind of data do you replicate? Are they close to each other? Are they far from each other? All these are different research issues, and they're application specific, they're workload specific, but different databases cater to different applications because of it. So there's a lot of research that takes place in these areas here. Now I'd like to move towards two other very popular technologies, and they're kind of different in what they do. One is Apache Hadoop. One is Apache Spark. Now Apache is this it's a foundation that lets you develop open source technologies. And interesting, my group is very heavily involved in working with Apache projects. They have a governance model, so they have a group of people who will manage the software. Typically, these are a group of people who are in industry. So a unique thing that has happened in the open source space over the last decade or so is that companies are volunteering the time of their engineers, their developers, to contribute to open source projects like Apache Hadoop, like Apache Spark, because they themselves are using these open source technologies. What they do is they contribute some of their time, which is unthinkable, really, that you have competing companies with software engineers, with hardware engineers, they are contributing to an open source technology. But this happens quite a bit now, and Apache is a leader in that. They're getting so many contributions, and then they have a governance team across industries. What that does, though, is that when students and researchers like my PhD students, when we download these software packages and when we provide patches to them, For example, when we fix some of the features, we patch, we understand how the software governance process works. So you can submit a patch, there's a governance team, they'll look at it, they'll give feedback, and ultimately that patch will be accepted and released with the main code. So students actually get an experience of what it means to work with the real software that thousands are using, and what it means to be able to understand it and make changes to it to contribute back to the open source community. That process itself gives them an understanding of what is the software life cycle in industry. And then they get to interact with lots of different experts in the industry, and often students actually just get jobs because the people in industry can look at your logs of how you have interacted, what contributions you have made to the open source technology and who's using it, and whether you've understood or not. So here's Apache Hadoop, and the idea for Apache Hadoop is that if you have a huge cluster of commodity nodes, which means not high-end servers, you take the data and you distribute it amongst these nodes, and of course you replicate them. And Apache Hadoop is very effective if you want to read the data once. So for example, if you're doing web search, so famously Google uses MapReduce, which is what Hadoop is based on. So if it has to do a search or any search engine, it needs to go through all the data it has and be able to search or compare your string that you have put in that search window, be it Bing or be it Google or whatever the search engine, your favorite search engine is. It needs to find a match for that string. As long as it goes to the document once, it's enough to find it. Now, if you are running a machine learning algorithm, for example, that's going to be iterative. It's going to take data and constantly iterate over the data, which means you read data, you write back data, you read, you write. So if you keep doing that, Hadoop is actually based on the disks. It has its own file system. You're constantly reading from the application level to the disk. You read, you write. It's very slow. But if you do it once, it's okay. So Spark is a technology that has come up, has become very popular now for machine learning, especially because it lets you iterate. And the way it does it is very simple. It reads once from disk, it reads everything from once, and keeps everything in memory. So the research with Spark is, how do you keep everything in memory and keep it fault tolerant? Well, you keep it on a cluster of nodes. How do you keep that fault tolerant? How do you replicate? How do you keep access to the data? And so on and so forth. And how big should your caches be? How big should your memory be? Because memory, again, it's a neat idea to put everything in memory, but remember, memory is very expensive. Once you go beyond 64 gigs to 128 gigs and beyond, the cost really escalates for memory. So you can't just have technology that depends on memory. So you have to be smart about how much memory you use, because you can have clusters and nodes, but you can't buy nodes, or I mean, it depends on your budget of how much memory you can add. So this is a competing technology, or not competing, sorry, complementary technology that works on iterative data. This is technology that works if you want to read once, but you have massive amounts of data that needs to be distributed and can be replicated. So typical examples are search, like grep, which is a Unix command, or if you want to do word count, those kinds of things work very well with Hadoop. If you have data on which you want to learn machine learning libraries, Apache Spark is very good. But the point is, these are all Apache technologies. So I want to highlight the fact that these are open source technologies. They are free. They're not only free for you to use, they encourage you to contribute back. So if you find a bug in it, if you find a new feature that needs to be added, you can submit a patch and then interact with the governing body of these technologies. So you understand how the software is actually developed and what are the challenges they will pose to you to prove that what you've done is actually a correct patch. So everything you've learned in your computer science curriculum, be it about testing, be it about algorithms, be it about performance, everything gets applied because you're experts in the industry that you're interacting with the moment you want to make a difference to these technologies. And we strongly encourage our students, especially our PhD students, to be working with these technologies and interact with the developers directly. So my group, for example, will have students who are posting to these blogs, who are posting how to use it. They're posting patches. They go in and do internships in these companies, and so on and so forth. I'll give you a very basic idea of how Hadoop works. And again, this is a very well-known diagram, well-known technology. So the idea here is that you have lots of words, and we're trying to count the frequency of words. Let's just assume that you have just a very small data set, but if companies like Google will be working at this at a massive scale, beyond terabytes, perhaps beyond petabytes, and so on and so forth. So they take this data and they split the data amongst lots of different nodes. And then they apply what's called mapping. So mapping is the code that you would write to grep or search for this. So on each node, you would search for these words and get a frequency count on each node. So again, remember, this is work that they're doing on commodity nodes, and thousands of commodity nodes, they're taking the data and they're running the same program, which is called the map program. So you would run map on thousands of these nodes, and each node then collects a frequency of words. Then you shuffle it based on the key, so the same word goes. Now, this shuffling again doesn't have to be thousands of nodes. It's ultimately up to research to say, how do you actually move data from this mapping to this shuffling, because shuffling is taking place again on nodes. Do you use the same number of nodes? Do you use less number of nodes? How much data is moving across the network now? So this is all the network data that you're moving. And then essentially you do a reduce and you come up with a list. So you can think of this as being petabytes of data, and you get and you get one small result. Or you can think of this as huge number of web pages that Google is indexing, or any search engine is indexing. And ultimately, when you do your search on something like Google, it has to go and search all these pages. And then, of course, they have lots and lots and lots of optimizations they have in terms of how they store the data, how they index it, and so on and so forth. But this idea of having this very simple functional programming paradigm, actually, this is not a new concept. This has been there in functional programming for a long time, the idea to do map and reduce. But now it's being used in cloud and big data at a very massive scale. Now, I want to talk about what are the research challenges here. So if you buy a very big cluster, suppose you have a cluster, or you are a cluster manager, or even if you have, say, $50,000 or $100,000 or whatever the currency is, how do you know what is a cluster you need to buy? How do you know how much money to spend on the processor? Because there are different generations of processors. How do you know if you need to have a mix? Should you have the latest processor on all node? Should you have a mix of these? What is a good way to invest your money? And once you buy it, you want to make sure it's used. For example, if you buy a cluster and half the time the CPU is idle, it's considered waste of money. Because you bought the machine, you want your CPU to be busy all the time with your application, especially if it's a data center. So how do you run algorithms? How do you design resource management software so that if you have lots of applications, those applications are actually going to be using, oops, sorry, I apologize. Those applications are going to be using the resources. Remember, the resources are very expensive, and the kind of environment we're looking at is a data center. It's a data center that's running, say, thousands of applications. It could be the Amazon data center, Microsoft data center, so on and so forth. All these companies have massive clusters, so many applications running. But if an application is running and it takes over a node, and let's say it's a 48-core machine, but it's only using 24 cores. So those 24 cores are getting wasted. So what the resource manager needs to do is to make sure that it distributes tasks so that these machines are at full capacity being used. The processor is completely being used. None of the cores are being wasted out there. And the idea is that you have lots of jobs that are there in the queue waiting to be run in the data center. How well you match these jobs with the resources that you have. Again, these are very expensive resources because the cost of your cluster completely changes depending on what kind of memory you have, what kind of processor you have, how much memory you have, how much energy is being consumed, how much is the disk being used, how much of the bandwidth you're using, because you're paying for each one of these. So Resource management is very useful. All cluster data centers will have it. I just wanted to talk to you about the flavor of research that we're doing in this particular area. So there are two basic technologies to manage data centers these days. I mean, that is being heavily researched. One is called Yarn, that works basically with Hadoop, and they're competing technologies. So Yarn is another resource negotiator. Just to let you know that I won't be focusing on Yarn, but Yarn is heavily used in industry. So if you have lots of different Hadoop clusters that need to be managed, and again, we're talking of resources that need to be managed. And how do you measure it? Well, if your utilization is very high, if your CPU is constantly busy, if your memory is completely being used, if your disk I/O is fully used, it means you've done a good job. If for the workloads that is coming to your data center, most of the time your cluster is sitting idle, or even some components are sitting idle, it means it's a massive waste of money. So cluster managers, computer science researchers are constantly looking to understand applications, their needs, and how to schedule them, how to manage the resources, understand how long applications take, and how they run. So I want to talk to you about a technology named Apache Mesos. This actually came out of Berkeley Labs. It's being sold, it's being commercially developed by a company named Mesosphere, but Apache Mesos is in the open source space. It's free to use, you can look at it. Now, the idea for Mesos is to allow resource sharing. What it does is it says applications shouldn't have exclusive access to nodes. So it allows multiple applications to live on the same node and execute on the same node. So it's kind of like virtual machines. So if you have virtual machines on the same node, they're isolated from each other. Apache Mesos has its own containers. You can also use Docker, which is a popular container mechanism these days. But what it does is it's essentially designed like a cluster-wide operating system. So imagine a cluster of 1,000 nodes or 10,000 nodes. Actually, it's been used for scales beyond it. It acts as if it is the operating system for the entire cluster. So it runs on top of Linux. And it's been working on Azure also. But assume it's running on top of Linux, and it's managing the resources of 10,000 nodes. All the number of cores out there, all the amount of memory out there. And then the way it works is it has what's called a Mesos master. It has all these agents or nodes in a cluster. So imagine there are 10,000 of these. Zookeeper, actually, we don't have time for it, but it's essentially a way for fault tolerance. It figures out which nodes have, which master has actually, is not responding. Maybe there's a network partition there. Maybe the node has gone down. It needs to do leader election to figure out which node is the master. So Zookeeper, actually, if you take distributed systems, Zookeeper implements the classical distributed systems algorithms. If you take operating systems, Mesos is doing the classical operating systems work out there. If you take algorithms, it's actually looking at different scheduling algorithms. So everything you've learned in computer science actually comes together with this particular technology here. So what it does is it's a master that talks to different applications. So think of Hadoop. Now Hadoop is a distributed application. So you could have an application that comes in, and it's very typical for Facebook or Twitter to say, an application to come to Twitter internally would say, I need to run some analysis, I need 20 nodes, and I'm going to use Hadoop for it. So Twitter has a massive cluster, it has user queries coming in, it has lots of internal applications that are also running. And that's also true for a university setup. If you have researchers in physics, chemistry, math, biology, computer science, they're all trying to run their applications on a shared data center. Then each professor will say, I need 10 nodes, I need 20 nodes, I need 30 nodes, and so on and so forth. So the idea with Mesos is you go and tell it what you need. So it has agents and all of these that are telling Mesos master, hey, I have 24 cores, I have 12 cores, I have 48 cores, I have so many gigs of memory, and you give it. So when a request comes in to say, from say one of the departments in this university that says, I need to run Hadoop. I need to run it on so many nodes. It goes to master, and the master is going to find it here for it. So the way it works is each node of the cluster will advertise to the master and say, I have so much available right now out there. And the resources actually in terms of number of cores, amount of memory, and the disk IO. And then what the Mesos master will do is to say, okay, you can use these particular nodes. You can use these particular nodes, and within each node, it will say you can use 4 gigs or 8 gigs, or you can use 12 out of the 24 cores, and it'll enforce it. So it'll give you access to fine-grained resources within nodes. It won't give you access to the entire node. And it will keep track that you asked for 12, it gave you 12 cores. If you try to access more, it'll kill your job. So essentially, it also uses containers, or you can use well-known container technologies like Docker, and it will provide you resource isolation. So it lets you share a particular node or set of nodes with multiple applications, and it's providing the underlying technology to keep applications separate from each other. But its idea is that it's going to try and do some kind of a fit. Now, if you've done operating systems, students would know about resource fragmentation and how when you keep getting memory can get fragmented. So the same thing can happen here, because applications can come and ask for different number of cores, and it's up to Mesos, and it's a configurable scheduling there, where it has to figure out which nodes to get all of this resources for and how many nodes. So that is what it does here. So where is the research here? Well, the research here is to figure out that you have different clusters, you have different applications, and you negotiate with the master. And the master is going to say, I'm going to give you so much, and you say, yes, I'll accept it, or no, I would not accept it. So there's a negotiation going on out there as to how many resources you need. And if there are multiple applications, there are different algorithms that are implemented. So the research is in what are the algorithms that you can write to share the resources, given that Mesos is giving you the underlying technology to keep applications isolated from each other. Once it keeps it isolated, it's up to you to figure out how to run it, how to make sure none of the resources are getting used. So Mesos is a perfect example of that, something that came out of a university research lab, and then they saw potential to it in a cloud setting, and now it scales for more than 10,000 nodes. It's used in so many different companies. Just some examples are Uber, Netflix, eBay, Twitter, Apple, and so on and so forth, PayPal. They use this. So their cluster runs Apache Mesos. And once it runs Apache Mesos in their huge data centers or the huge clusters, very large scale clusters, we're talking of more than 10,000 nodes. I think I've also heard that Apple Siri, where you ask questions, also runs Mesos, because it's constantly getting requests and it needs to manage all the computing resources it has. So it goes with it. Now, what else does Apache Mesos give you for research? It gives you different kinds of counters. So it'll tell you how many tasks that you launched that failed, that for some reason the node didn't start up, the node failed, maybe the task itself failed, maybe the task got killed. It will tell you what are you using. So if you launch tasks and you say that you wanted 4 gigs of memory, it will tell you how much you're actually using. Because you may be asking it for it and Mesos will believe you, but it'll give you feedback that you actually only use 3 gigs or 2 gigs or so on and so forth. So what it does is it lets applications for the next time figure out how much they should really ask and keep the cluster well managed. Well, so that was just the underlying technology. So what we've done is to say, okay, we have Apache Mesos that gives you this basic framework that's being used by industry, that's shown to scale for more than 10,000 nodes. So many companies are using it now for the different applications. What can we in academia do? What can we do research with? Well, there are lots of different things we can do with just the resource management aspect for it. Remember, Mesos just gives you a framework and you can write your own algorithms of how to share the resources, which ones to accept, which ones not to accept. So deadline-based scheduling, for example, if you have lots of tasks and all you need to know is that by 8 a.m. tomorrow, you want the results for these 10 particular tasks that you've given. For example, if the results are going to be declared tomorrow, you just want to say in the cluster, we'll calculate all the percentages, aggregates, ranks, and so on and so forth, but it needs to be done by 8 a.m. tomorrow. And there are different requests from all across campus, from physics and chemistry. So deadline-based scheduling says it will decide how to order these particular applications or requests so that everything gets done by 8 a.m. Because then it's a challenge of what is the sequencing for your applications. Because remember that, for example, if you have 48 cores and you have one application that needs 24, the other needs 12, maybe if something else needs 10, you can try to fit all of these into the same node. But if you take two applications that have 24 and 24, then an application that needs a few cores will have to wait for the rest. So there's starvation. So they're classical operating system scheduling problems. But here, the resources are multidimensional. You're not just looking for processing cores. You're looking for memory. You're looking for disk I/O and new things. Maybe you're looking for network bandwidth too. All of these are resources that are shared in a cluster. The applications can interfere with each other. So sequencing of applications or tasks or jobs that you have to run based on a deadline now becomes a challenge because you have to estimate how long will the applications take to run. How much will they really use? They're asking for something, but will they really use those resources? Which resources do you think they will actually correctly use, and maybe they won't use memory as much, or maybe they will overshoot the memory, maybe the task will fail, and so on and so forth. So deadline-based scheduling in this massive scale gives you an opportunity to do research. And remember, the scale is such that network could get partitioned, some nodes could die, disks frequently fail. So you have to take everything into account, and then you could do some deadline-based scheduling. Again, you would decide saying, these are the workloads that are very specific to this particular university, and this is how you should do it for that. You could try to get throughput because you want to get more and more applications completed early. It couldn't be deadline-based. How do you do that? Because you're sharing. Remember, as long as an application is running, you cannot take it out. So how do you order these applications and how do you let them share the resources is a very big problem. Energy aware, I'm going to talk about energy aware scheduling. The data centers cost a lot of money these days just to cool them, just to run them. It's a very big part of the budget. So keeping a data center cool, the amount of money that is spent on just managing a data center, the power consumption is enormous. So how do you try to get throughput, try to get good performance, but keep the cost low? Because energy is such an important component of data centers and clusters these days. And high performance computing, for example. Now, there are some trade-offs here. For example, if you really want high resource utilization, for example, if you say, I want to keep the CPU busy all the time because I've paid so much money for it, then it'll start drawing more power. So they keep the CPU busy, it draws more power, that's more energy out there. So there are different kinds of trade-offs that you will have. And if you reduce utilization, for example, you say, you know what, I don't want everything to be used because I want the energy to be low, then applications will run longer because you've slowed down everything. So there's a trade-off. The question is, how do you manage these trade-offs for a given set of workloads or for known applications that are running in industry, because it can save you huge amounts of money, huge amounts of time. That is where the research challenges are in the big data cloud resource management. There's so many questions that need to be answered here. Why is energy consumption such a big problem? By some estimates, 3% of the global electricity supply is going to data centers. That's very, very high. So imagine the amount of cost, the amount of money we're spending on just managing these data centers that is at the center of our lives these days. There's an estimate that it will grow up to 300% of what it is now. Now, if you try to keep your machine running all the time, I'm not sure if you guys have experienced it, but you see the disks fail. So the hotter the machine gets, likely the chance that maybe the disk will fail, maybe the processor will fail if you keep it hot for a very long time, which is why we have cooling mechanisms for laptops, for desktops. We keep them raised platforms. Data center cooling is very important, but you try to improve the utilization and maybe the machines will start failing. So all kinds of different challenges that you have to face, and to prevent them from failing, you have to cool them. Cooling them again takes a lot of electricity out there. So we have classical trade-offs, which is ripe for research for us. Again, just a chart on what it's costing. So if you increase the size of your data center, the cost per kilowatt goes down, but it's still significantly high out here. If you have greater than 50,000 here in terms of your data center size, it's still going to cost you quite a bit. So even these numbers are enormous in terms of the cost of the data center. Obviously, running a very small cluster is very expensive. As you keep growing, maybe the cost gets amortized a bit, but it's still at a point where it pinches quite a bit. So energy consumption, and there's a lot of research on energy consumption, data center management. We have different professors in our department and across the research community that work on different aspects of it. I'm going to talk about a very specific, narrow aspect of it today, just to show you that this data center cost in terms of energy is so high. So when you have cloud computing, when you have data centers being run, whether you're checking email on Gmail or Yahoo, they're all being run by data centers. And they're massive because they're accessible across the globe. They're replicated across the globe. There's search, whether it's YouTube, whatever it is, whether it's Facebook, they all have data centers. So it's a problem that's universal. And whether they use Apache Mesos or not, they're using something equivalent. I think Google uses Omega. So that the equivalent resource management softwares that they're using, and they're all facing the same challenges of trying to keep the utilization high because they're paying money for it, and then keeping the costs down. Now, I'd like to slowly explain this diagram to you. So what we have done is to build something on top of Apache Mesos. So Apache Mesos is this resource management framework, it's a data center operating system, but it lets you submit jobs to it in a very customizable framework. So there are well-known ways of doing it. One way is called Apache Aurora. What it does is it takes jobs from you and submits it to Apache Mesos. It works with Mesos directly, so if you're happy with it, you can use it. But since we want to research, especially because we want to say how can we work with different scheduling algorithms, different ways in which we can reduce energy but not get hit in terms of make span or throughput. I just want to give you some flavor of it. So what we do is we use what's called RAPL counters. So this works only with Intel technology. So with Intel processors, it gives us very detailed information of how much power is being used. I think we poll it every 1 second. And Performance Copilot is actually, I think it's in the open source. What it tells us is the usage metrics. So it will tell us that this is the amount of memory this machine is using, this is the CPU utilization, and so on and so forth. So what we have done is to install this on all the Mesos nodes that we have. We have a small cluster of 200 cores on which we do research. So we've installed it everywhere. And our research that we want to show you here is looking at two different things. One is how do you schedule? So when you have jobs and you have lots of nodes, how do you decide which node to place a particular job on, depending on what resources it's asking? How do you take into account the power it's consuming? Because every second we have a way of measuring how much instantaneous power is being used. We also have a way of saying we want to clamp down. So you can take a particular processor's TDP and say we only want to use 50% of it. So you can clamp down processor, essentially slow it down. 50% or 75%. We have a way of capping the power that a processor is using. Again, it's provided by the hardware manufacturer itself. So we take into account that we can control how much power is being consumed by essentially reducing it. We can schedule however we want on it. And then our aim is, can we reduce the energy usage? But do not take a big hit on make span. Remember that you can just slow down a processor by 50% and increase your running time by 2 times. So it is a very fairly easy thing to do. But the challenge is, how can I not let my runtime increase so much but still gain on energy? And the key idea here is that if you take 2 applications and run them separately, they will take more power compared to if they run together. So if they run together, there are lots of things that they can reuse. Perhaps they can reuse the file system, and the clock, when when it's already in a high peak state, the processor is going to continue working very fast for the second application as a switch. So what we want to do is, given that Mesos allows us to co-schedule, remember, it will allow you to put applications, 2 different applications on the same node. Of course, it provides protection between them. So we have to decide whether the second application goes on the same node, the third application goes on the first node, or it goes in a new node. So how do we distribute the load that we have while constantly trying to keep our power consumption? Now, we've all understand energy consumption, but one key requirement here we have is peak power. Let's say, applications, when they run, the power consumption goes up and down, right? They peak at some time, they go down, they peak again, then there are high peaks and low peaks, but the power consumption is not uniform. It goes up and down. Now, let's say we have lots of applications running on, say, 10,000 nodes. If all the applications peak at the same time, there's a power surge. If there's a power surge, it'll trip a breaker somewhere and there'll be a power outage. So the way we want to do is to make sure that applications don't peak at the same time. So we want to look at these applications and say, let's just make sure that they are peaking at different times. So maybe you can schedule something 5 seconds late or 2 seconds late, or try to find what are the good co-runners of different applications. Now remember that if you have lots of applications and they all have power profiles, just getting the power profiles and combinations, every possible combination cannot be tried out. So it has to be a heuristic mechanism that we do. But for data centers, it'll really make sense to tell the utility company that, by the way, tomorrow between 2 p.m. and 5 p.m., my cluster will not breach this particular power envelope. So if a cluster can give that guarantee to the utility company that I will not breach it, so utility company can plan and say, okay, this is the power draw that will come from this data center. So our research is focused on saying, how can we keep the power envelope contained? Because we have a mechanism of bringing down the power of each node. So we're dynamically trying to understand how much is the machine being used and try to bring it down. So I want to talk to you about scheduling policy. How do you actually place tasks on nodes? And how do you cap power, given that each node can be capped? So we want to study the combinations of different things. I'll show you 2 different algorithms, 2 different extremes to show that the optimization space is there. So this presentation is to tell you there's opportunity for research here by showing extreme cases and showing everything in the middle you can work on. So let me talk about 2 different ways of doing it. So one is first fit. The first fit is a very normal algorithm. This is what the default Apache Aurora does, but this is the naive way of doing it, is to say the moment you get some resources, find the very first task that can fit within these resources and just go and run it like that. The other is also the classical bin packing. Again, I'm trying to show you the 2 different extremes. Bin packing is to say, what are the maximum number of jobs that I can actually put in a particular node before I move to the second node? So remember, the first one is just trying to find a fit and it'll spread it across the cluster. The second is to say, I'm going to pack the bin. And bin packing is a classical algorithm. In fact, it's an NP complete. If you look at the different resources that are there and what you're trying to bin pack out there, it's an NP complete problem, which means you cannot possibly in polynomial time come up with a good solution for this. So we try to have some heuristics of how we will do bin packing. In fact, we've shown this is a multidimensional bin packing problem. So we have a classical computer science bin packing problem where you say, okay, we will not go to the second node till we have exhausted running everything in the first node, and then the second node, then third node. as opposed to first fit that just spreads essentially. Now, this is again, remember I'm trying to show you the methodology of research. We try to do the extremes and try to understand what is the optimization space there. Is it really possible to have a good power envelope and actually see how much we get hit on make span? So what I want you to notice here is actually, so this is how the shape of, so this is essentially the power that is being, the Rappel power that is being used, and this is time. So as the applications keep running on the cluster, this is a 200 core cluster, we have 8 nodes there. So essentially what I want to show is bin packing reduces the power envelopes. The green out here is bin packing. So what you want to see is that we can actually bin pack and say that we want to put as many as we can based on the power profile before it exceeds the TDP. So we know that an application will take, say, 50, and some of the applications will take 50. We know the combination is going to take less than that, and the manufacturer says you should not, say, breach 120 or 100. So we know how many we can bin pack. So we keep trying to push into the same bin, which is a node here, and we see that we can control the power here. We are able to keep controlling. The green shows that the power envelope of this particular strategy of bin packing is much lower than if you don't do it. If you don't do it, it keeps spiking. Remember, spiking is not good because if all the nodes spike at the same time, there's a surge. So we want to reduce it. We want to be able to give the guarantee to our power provider, electricity provider, that we will keep within a certain limit. Well, we're doing that here, but look, there's a small increase in make span. So the question is, what is the trade-off? Is this slight increase in the amount of time worth it because you're reducing the cost of running the cluster so much? And remember, this is now again important when you do some research like deadline-based scheduling. If you do deadline-based scheduling and then you have the constraint, do not use too much power, you know that if you're using this basic technique of bin packing, this is the extra time that your application is going to run. And in this particular case, compared to, say, the first fit out here finishes at 1400, this finishes at 1600 seconds. So it's taking 200 more. So it is a big hit. It is a hit, but maybe not as big a, the advantage of power here is much more here. And we also show the energy. The energy consumption, again, is essentially the area under the curve here. So there's a very slight gain in terms of overall energy gain. Now, I want to show you another example. So actually, we call what we call is extrema capping. So in static capping, what you could do is to just say, I will make sure none of the processors go beyond 50% or 60% or 70%. Well, that's a naive approach. Again, we're trying to test the boundaries of what we could do. In extrema, which is a slightly better algorithm, we'll say that we want to keep a power band. So we want to have a low threshold and a high threshold of the power. So we set some threshold and say that for this particular processor, we do not want to exceed this threshold. And the moment we keep calculating the power being used across the cluster, because we don't want the overall spike to be high. And the moment we see that it's coming close to our high threshold, we start capping the nodes one by one to reduce the power. And when it goes below the low thresholds, very easy, we start uncapping. So essentially, once you come up with what is a good power band that you want to keep in and that you could do with a connection with a utility company and say, this is what we'll keep it with, we're showing that in software here, given Apache Mesos, given a research environment, given the framework we've developed, it is possible for you to control an application as it runs in and keep it within a power band by constantly capping, uncapping. And the research is actually selecting the nodes because the applications is running across the cluster, selecting which nodes you want to reduce slowly. You have to keep reducing the power and then increasing it so that you don't get a hit on make span. So here we want to show that if you see the green here, you see the green is going much below. Again, y-axis is power. So we're showing that the green here has a much better power envelope because we are improving how we're keeping it low. Again, we're constantly monitoring the make span. So given it's an NP-complete problem, we are not able to, it's heuristic as to which application should be run with which other application. So if you have like 25 applications in the queue, deciding which 2 applications are good co-runners is actually a tremendous challenge. But you could have some static profiling, or what you're showing here is you could do dynamic profiling too. You can constantly monitor the applications to figure out how to match the 2. And it's not always possible to do static profiling, though we did profile them initially here to get an idea. Now, again, we look at some well-known algorithms. So one is a max-min. Essentially, it says, how do I schedule tasks on a particular node? We'll say, well, we'll pick an application that has a maximum power draw. And then we'll pick the next one that has a minimum. Then we'll have another one that's max-min. We keep alternate between the 2. And then the other way is, well, we'll pick the highest and then we'll get as many low ones as possible. Again, we're trying to show 2 extremes because you have to heuristically select, given it's an NP-complete problem, heuristically select which applications to run, which applications to run with each other. And we want to study and let the data drive the next research here. So what we see is that if you do max, min, so on and so forth, and if the workload is all light, if you do not have really high spiking workloads, if the workloads are all moderate in terms of how they behave, then if you take max, min, if you keep alternating between taking the max and minimum in terms of each node where you schedule them, it does a good job of reducing the power envelope. This is the red here, you see that? But then you see it gets a hit on the make span. Again, for us, it's about quantifying this make span so that that data can feed into deadline-based scheduling and so on and so forth. And if you take one max and try to get in as many mins as possible, remember you're trying to take power profile, and then you're trying to take applications that draw a lot of power and then mix it with those that take very little power from the queue. What it does though is it reduces execution time as it distributes the tasks very well, and for a light power consuming node. So as long as it's light, it's okay. But what happens is when it is moderate, like it's not very high peaking, what it does is we see some dampened effect with the max greedy mins out here. And max min continues to maintain a low envelope. Interesting thing though is that if it's a lot of workloads that all seem to spike a lot of power, how do you schedule them? Well, we studied them, and what we see is that then it is best to actually have a max min mix, because if you have max greedy mins, what happens is that the high ones keep starting later and later, and if they keep starting later and later, this is the green here, you have the effect on runtime here. And the power envelope, it stays high for a longer time for us. So actually I'll skip. So essentially what we want to see is we compare our results and try to see what happens to just the envelope of the power as it goes, and we try to study the shapes of it. And we see that the algorithm that we have come up with is still allowing the applications to peak a little bit here, out here. And we don't want the peaks, because peaks, if they all come together, if they're aligned across the cluster, it's a big surge for us. Again, we cannot predict. So we've been working on something known as progressive extrema, that it's trying to actually reduce the peaks that is there, because it dynamically changes the power band that we have out there. So this is the current research we have as to how to keep the peaks much more aligned to each other. Now, I want to show this research to say that what are we doing? We take Apache Mesos with open source technology that has so much traction in the industry. And we say that, well, they're working with just amount of processing cores, amount of memory and disk IO. Our goal is to say we have all these results in research, and then we want to let you schedule. So we want to add code back to the open source community and say, well, we're going to add one more parameter, and that is watts. So what we want to do is we're working to be able to contribute back and say, you can actually schedule not just on the classical parameters that are there, but you can specify the watts and say, I want my application to get so many watts when it runs. Or you could say, I want my application to take so many watts along with, say, 10 or 20 or 30% leeway to say it's okay if you reduce my wattage by 10% or 20%, but let users decide and let users give you a hint, because you may be doing deadline-based scheduling. Let users give you a hint about what is their tolerance in terms of how much power you let their application draw, and make power a first-class parameter in terms of scheduling for massive data centers, because energy is such an important parameter. As of now, it is not being done. As of now, it's not part of the scheduling. We have actually we have implemented locally, and our work right now is to be able to patch this with what the open source community is using. It's what industry is using. And as we come across, we publish the new algorithms that we come up with. We publish the new insights that we develop in terms of applications and in terms of application workloads, in terms of the classes of applications. So we can classify applications depending on their power draws, not just on their throughput. And then we say, this is how the cluster's overall energy is going to go down. So I just want to quickly talk about one more slide, one more research. There's a complete different, because I mentioned NoSQL. We work a lot with flash arrays, because the idea for IBM is actually to do what's called big data in a box. So they would like companies or customers and clients to buy their technology with flash arrays, because flash array speed is somewhere in between memory access and disk access. So memory access is very fast, but it's very expensive. So if you want to buy a cluster that has, say, 40 terabytes of memory or 80 terabytes of memory, it's cost prohibitive. So what IBM is working on flash arrays is to say, well, you can still get 40 terabytes of flash array. So that's going to be slower than memory for sure, but it's going to be way faster than having 40 terabytes of disk. So then they have developed what is called Capi Flash, which gives you direct access to the flash array. And our group here works on taking technologies like Cassandra and MongoDB, and instead of writing to disk for all the commit logs, it directly writes to flash array and gets a huge percentage improvement. So, for example, my PhD student who's been working very close with IBM research is showing a performance improvement of 650% as opposed to the classical deployment of Cassandra, which uses disks. If you use IBM's flash arrays, so if you want to scale out your big data technology instead of having massive clusters or a lot of memory, which is expensive, this solution is to say buy a flash array, which is orders of magnitude cheaper, but you will get such amazing improvements. So that's one of the research that we're working on.